Hello, we are group number 5. Our topic is analyzing key factors influencing housing value in Boston, Massachusetts, and the group members include myself, Maddie, Jenna, Rajesh, and Mason. To give some brief background on our project, our main purpose was to conduct an exploratory study to determine the key factors that influence the monetary values of home in Boston. The primary end goal being to explore the impact of 4 distinct dimensions to determine the best model for predicting the response variable Y, which is this median home value. Research question 1 investigated the first dimension, socioeconomic influence. Research question 2 investigated the second dimension, physical housing and neighborhood characteristics influence. Third question investigated the third dimension, environmental influence. And the fourth question investigated the fourth dimension, location and accessibility influence. Here you can also see a brief data introduction. We obtained our data set from Kaggle, which is an open source platform of diverse data sets that users can explore with various different methods. And here's also a list of our variables that will be delved into deeper through each research question. Also, anytime we mention alpha, it is 0.05.
To begin with research question 1, we sought to understand how socioeconomic factors such as crime rate, property tax rate, pupil-teacher ratio, and the percentage of lower status population all impact housing prices. Our null hypothesis stated that none of these factors significantly affect housing prices, while the alternative hypothesis suggested that at least one predictor does have an effect. We explored a full model using these variables and began our analysis by checking the relationship between them and the response variable, housing price, using scatter plots, correlation matrices, and residual plots. This preliminary analysis allowed us to identify key issues like nonlinearity, multicollinearity, and heterostaticity. In step 1 and 2, we performed several diagnostics to ensure our model met the assumptions of multiple linear regression. We confirmed the independence of errors through residual plots. However, our analysis revealed 2 major assumption violations: normality of errors and heterostaticity. To address non-normality, we used bootstrapping for parameter estimation. Heterostaticity was resolved using least weighted squares after applying logarithmic and exponential transformations to x1 and x13. After these transformations, we continued to refine the model and improve fit to address the violations. Step 3 involved hypothesis testing on the improved model. We conducted general linear tests for predictors x10 and x1. The results showed that both variables were not significant, with p-values of 0.62 and 0.41 respectively. Based on this, we removed them from the model. The final refined model included only x11 and x13, as these 2 predictors showed significant impacts on housing price. When we proceeded to confirm this refined model through further diagnostics, ensuring that all assumptions were met, particularly focusing on heterostaticity and non-normality. Step 4 focused on identifying the best performing model. Using the best subsets algorithm, we determined that the final model, yx11 plus x13, was the most predictive of housing prices. The model was validated by its low residual sum of squares value and its solid performance across various selection criteria, such as adjusted R squared and AIC. Furthermore, cross-validation showed that this model provided the best balance between complexity and predictive power. With this validation, we were able to confidently select the best model for our research question. Step 5 and 6 of our analysis focused on the final validation of parameter estimation. We used tenfold cross-validation to ensure that the predictive accuracy of the reduced model, which achieved the lowest RMSE. Bootstrapping was applied to estimate the confidence interval for the model's parameters, confirming the robustness and stability of the coefficients. These results, combined with the strong performance and cross-validation, solidified the final model. This model explains how socioeconomic factors, specifically pupil-teacher ratio and the percentage of lower status population, significantly influence housing prices. In conclusion, our analysis of socioeconomic factors influencing housing prices in Boston revealed that the pupil-teacher ratio and percentage of lower status population were significant predictors, while the crime rate and property tax rate were not. These findings align with common sense, as areas of lower socioeconomic status and poorer educational resources tend to have lower housing values. However, the exclusion of other potential factors, such as proximity to anemones, limits the scope of our future model. Improvements could be made incorporating more predictors or exploring interaction between different variables. This model provides valuable insight on the socioeconomic influences on the housing market in Boston.
Research question 2 asks the following question. Given physical housing characteristics, which is the average number of rooms per residence, have significant impact on housing value, do neighborhood characteristics such as per capita crime rate by town, proportion of non-retail business acres per town, proportion of owner-occupied units built prior to 1940, pupil-teacher ratio by town, and proportion of people of African American descent by town have significant impact on housing value. The purpose of this research question is to explore the impact of our second dimension, physical housing and neighborhood characteristics influence on housing value. In my model exploration process, I made a pairwise scatter plot and computed the VIF values. I performed diagnostics which showed that the error terms are independent, but error terms do not follow a normal distribution and there is constant variance issue. Remedial measures were performed, including a transformation on x1, x3, x6, and x7 based on scatter plot results. Squaring these predictor variables did not fix constant variance issue, and doing a square root transformation fixed constant variance issue, but significantly reduced the number of rows without missing data. I tried the similar transformations on just x1 and x3 and had the same issue as well. Because of this, we continued with hypothesis testing with the original model and decided to improve the model and run diagnostics post-hypothesis testing. The GLT test on the left confirms that the given condition is valid and x6 is significant. We reject the null hypothesis and conclude that at least one of the predictor variables is significant to the model. The summary of the full model on the right shows that x3 does not have significant impact due to the p-value greater than alpha and should be dropped from the model. Using best subsets algorithm, I confirmed that x3 should be dropped from the model due to the low press p-value. After confirming that x3 should be dropped from the model, I performed WLS on this reduced model and computed the BP test, which confirmed that constant variance is fixed with a p-value of greater than alpha. The tenfold cross-validation shows that the reduced model without WLS is actually the best model due to its low root mean square error. I used bootstrapping on this new model to get parameter estimates of the model, and you can see on the bottom is my final best fitted model. The results of the hypothesis are that given physical housing characteristics, which is the average number of rooms per residence, have a significant impact on housing value, neighborhood characteristics such as crime rate per capita by town, proportion of owner-occupied units built before 1940, ratio of pupil-teacher by town, and proportion of African American residents all significantly impact housing value. And the proportion of non-retail business acreage per town does not have a significant impact. This model was confirmed by best subsets, but it was not confirmed by cross-validation. Cross-validation actually confirmed that the reduced model without WLS is the best model. However, non-retail business acreage per town is still determined as insignificant by cross-validation. Limitations of this research question is that normality and constant variance were not fixed prior to hypothesis testing. In future studies, additional advanced remedial measures should be performed to the model prior to hypothesis testing.
My name is Rajesh Nandi. So my research question was, given that the residential land zoning has a significant impact on housing value, does nitric oxide concentration have the same impact on housing value depending on the river proximity? In other words, is there any interaction between nitric oxide concentration and river proximity on housing value? So this research question is important because it examines how environmental factors like nitric oxide pollution and proximity to natural features like a river interact to influence the housing values. By exploring whether pollution impacts property values differently based on river proximity, the study provides insights for urban planning, zoning, and environmental policies. So here is my hypothesis setup and full model and the reduced model. So my response variable was median value of owner occupied homes, and I used three predictors x2, x4, x5. So x4 represent the proximity of a river from the property, and it was a categorical variable having two labels 1 and 0. X5 is the concentration of nitric oxide, and X2 is the proportion of residential land zoned for lots larger than 25,000 square feet. So my aim was to check the interaction between X4 and X5. That's how I set up my hypothesis here. Next, I started with the full model. So here you can see the pairwise scatter plot and the correlation matrix. Both confirms that I didn't have any correlation among the predictors. Then I calculated the VIF values for different set of predictors, and I found that all the VIF values were less than 10, indicating I do not have any multi-collinearity issue. Then I checked the independence, which was okay. Then I checked the normality. You can see that some points at the tail of the QQ plot are of the y equal to x line, and also the Shapiro test showed the p-value less than 0.5. That means I have issues with normality. Next, I check the constant variance here. You can see the plot for residuals on y hat and other predictors, which seems okay. And also the p-value was greater than 0.05, which indicates I do not have any issues with the constant variance. You can also see the influence plot here. I have some influence point. So to remedy the normality, I used different transformation, Box-Cox, power transformation, logarithmic transformation. All the transformation showed that it slightly improved the p-values, but it led to constant variance issues. So I didn't proceed with the transformation. Here are the results from my hypothesis test. So I conducted a GLT test and found that the p-value was greater than 0.05, indicating that the interaction term doesn't have any significant impact on the model. Next, I checked the main effect of each predictor and found that they all are significant for the model. So I proceeded with the reduced model and checked all the diagnostics and found that the model has issues with normality and there are some influential points. As a remedial measure, I used some transformation, but it didn't improve the model. Then I excluded the influential points, but it also didn't improve the model. So I also used the robust regression here, as it can dampen the effect of influential points. Here I select the best model from best subset algorithm. Here you can see that the selection was based on the lowest value of price, as I am predicting some future prices. So interestingly, this highlighted model also showed highest adjusted R-square value and lowest CP, AIC, BIC and price value. So this is the best model according to the best subset. Here I validated the model using 10-fold cross validation. So for the reduced model, I had the lowest value of root mean square error. I also applied bootstrapping as I had normality issues, and this is my final model. So overall, there was no interaction effect between nitrous oxide concentration and the river proximity. However, each predictor significantly influenced the housing prices, and the predictive power of the model was low, as can be seen by low value of R square. This is because I didn't include all the variables in the dataset. So the future study should include all the variables which can better capture the full range of influence on housing values.
Research question 4, investigating the fourth dimension, location and accessibility, is as follows. Given that the full value property tax rate has a significant impact on housing value, does weighted distances to 5 Boston employment centers have the same impact on housing value when the index of accessibility to radial highways is low versus moderate to high? In other words, is there no interaction impact between distances to employment centers and accessibility to highways on housing value? Here you can see my initial hypothesis setup with the MLR full model as well. The response variable is the same across all research questions, and my X8 variable is the distances to the employment centers in Boston, X10 is the property tax rate, and X9 is the indicator variable measuring the accessibility to radial highways grouped into 2 levels, the baseline measuring the low accessibility, and X9 equals 1 representing moderate to high accessibility. The first step to my process was model exploration and diagnostics, as well as remedial measures on that original full model. I did a pairwise scatter plot, which shows some curvature between y and x8, as well as y in the interaction term. The correlation matrix in the VIF revealed no multicollinearity issues, and an added variable plot revealed little or no added on effect for x8, which will be discussed later. Diagnostics test revealed that the error terms were in fact independent. However, the Shapiro-Wilk test showed that the error terms were not normally distributed, and the Bruce-Pagan test confirmed the errors did not have constant variance. I also did an influence plot, which identified some influential cases, but that will also be discussed later. Remedial measures first began with standardizing my continuous variables to eliminate any potential issues that could arise from those being measured in different units. However, this did not change any of the exploration or diagnostic results. I then attempted some transformations on y to address the assumption violations. However, transforming y as well as combining a transformation with y and x didn't solve my violations and actually made my constant variance worse. So then I tried to only transform x8 as indicated by the curvature present, and I did x8 squared or exponential x8, and both of these achieved constant variance variance. However, I decided to proceed with x8 squared in my model, as putting this in the model had a lower MSE than the other transformation. I then reperformed the diagnostics and showed improvements in my new model that I will proceed with in the following slide. My next step was then hypothesis testing with this improved model, and of course I confirmed my given assumptions validity by generating the R summary table and confirming X10's marginal significance. I then did the main GLT test, testing the interaction effect, and found that we failed to reject the null hypothesis and conclude that the interaction effect is not significant because of the F test statistic being less than the F critical and p-value being greater than alpha. In other words, we found that the weighted distance to employment centers has equivalent impact on the median value of homes, regardless of the accessibility. I then decided to investigate the main effects of X8 and X9, beginning with X8 because of the added variable plot assumption and observation showing no added on effect. And after performing this GLT test, I determined that X8 can be dropped from the model already including X9 and X10 because of the same rejection region conclusion. I then confirmed the marginal significance of X9 and X10 before proceeding as the initial best model before I continue with my steps by doing the R summary table. Therefore, in order to really confirm that the reduced model I just showed is indeed the best subset of all possible predictors in my dimension, I performed the best subset algorithm. And looking at the lowest pressed p-value, I was able to confirm that the model only including X9 and X10 is indeed the best subset in terms of predictive capability. Then I performed model exploration, diagnostics, and remedial measures again on this after this conclusion, and I confirmed X9 and X10's marginal significance and linearity with the added variable plot, and I also confirmed that X9 and X10 are independent with no multicollinearity issues, as well as the error terms are still independent. However, the non-normality of error terms violation, that is still present in this model, but the error terms now do have constant variance as indicated by the results of the BP test. Finally, as my last two steps, I did model validation and parameter estimation. I performed the tenfold cross-validation between candidate models and found that the lowest RMSE value was for my reduced model, validating that this model is indeed the best for predicting Y in the location and accessibility dimension. I also did include the robust regression of this model in my tenfold cross-validation and still found that the model without dampening influential cases was the best and proceeded with that. I then applied bootstrapping to this model for accurate parameter estimations in the presence of non-normal errors that were not able to be addressed with transformations previously. And finally, my best fitted model for this dimension is presented here. All in all, the key findings of my research question was that no significant interaction effect was found between distance to employment centers and accessibility to radial highways on housing value. In fact, distance to employment centers was found to have no significant marginal effect. Therefore, the final model that we validated includes only accessibility to radial highways with a positive marginal effect and property tax rate with a negative marginal effect, which aligns with intuitive expectations and common sense. Limitations were the fact that non-normality of error terms was not fully resolved. However, this was deemed acceptable due to large sample size and the use of bootstrapping for parameter estimation. Influential points were also present but not addressed as their impact was deemed negligible. Recommendation, therefore, for future studies would be to develop and validate a full model using all variables across all four dimensions for a more comprehensive analysis initially, as well as focusing more attention on exploring advanced remedial methods to address the non-normality and to handle the influential cases effectively. Finally, to tie everything together, we performed another tenfold cross-validation among all of the best models from each research question as listed again here. The lowest RMSE value was associated with the best model from research question 2, and therefore our final best model was associated with dimension 2, physical housing and neighborhood characteristics. And we determined that this is the best dimension to consider in regard to predicting the median house value in Boston. This aligns with common sense expectations, but is subject to the limitations that was acknowledged for this model during the discussion for research question 2. Lastly, as a final discussion tying everything that we just did together, our main key finding of this project was that physical housing and neighborhood characteristics, Dimension 2, demonstrated the strongest predictive capability for meeting housing values in Boston, as identified through the cross-validation procedure we just talked about. Practical insights for our project is that these results emphasize the critical role of structural and neighborhood-specific factors in shaping the housing markets, surpassing the predictive influence of all of the other dimensions. Audience impact for this project is that the study provides actionable insights for stakeholders in real estate, urban planning, and policymaking, all in all enabling data-driven decision-making to improve housing value by prioritizing the key predictors in Dimension 2. The limitations of this study is that there are some unresolved assumption violations like the non-normality of errors, as well as the isolation of the dimensions, which may impact model reliability and interpretation. Therefore, future directions for future studies is that they should explore integrating the variables across all dimensions initially into a unified model to capture interactions and refine the predictions. Additionally, we should focus on advanced remedial measures that address the assumption violations that we could not address for enhanced accuracy and robustness. Finally, our main contribution of the project is that its systematic and data-driven approach offers a clear framework for identifying influential factors in the housing markets and sets the stage for more comprehensive analysis in the future.